Hi, I'm Colin O'Flynn, and I'm here to talk to you about fast-tracking your DPA testing. So you might expect one of these sponsored sessions is just going to try to sell you on something. Yeah, sure, that's the idea, but what I'm actually showing you here is a bunch of open source tooling that I've worked on. So a bunch of this you can actually use freely, so it's freely available. We have some resources, some tutorials, some training that were primarily designed to actually help people understand DPA testing and understand some of the work that you might need to do in setting up your own sort of test environment, or if you're outsourcing stuff, really understanding how it works on a pretty low level. So that's kind of what we're here to talk about today. So differential power analysis, right? Differential power analysis has been around for a while, so theoretically you already know what it is. But really briefly, the idea is that you have a cryptographic core or some sort of core that's processing some secret data. Over here we have, a microcontroller. And this microcontroller, for example, we have a really basic measurement set up where there's some shunt resistor that lets us measure the power flowing into it. This gives us some waveforms where we can observe the power being used, and the power being used has some relationship with either the operations being performed with simple power analysis or the actual data itself with differential power analysis. And this is extremely powerful way of breaking cryptographic solutions. So it's been integrated in many different cryptographic test suites and standards for quite some time. But of interest probably to a lot of people is with FIPS 140-3, it's actually becoming probably more mainstream than it was. We're also seeing sort of what I call consumer devices, so devices that are widely accessible on the open market, also integrating DPA countermeasures. So it's something that's, if you're not already working with it, you're definitely going to be in the next little bit. So a short history of DPA, right? We have it introduced in August 1999, or maybe before that, but that's the actual conference talk. And we're now in September 2020. So what's that between it? Well, that's more than 21 years, actually, just over 21 years. So, the question is, surely by now you've done some work with DPA, right? Because it's been around for 21 years, so surely you know about it. And what I sort of found is that, while some people are working with it, there's lots of people that think it's complicated to get started or expensive or things like that. So part of that sort of the reason that I created this project called Chipwhisper, which is basically open source. It started as actually research tooling for myself, but it's open source tooling, so it's the first open source tool chain, I say, because it includes hardware, software, and documentation. So you can actually use it to understand a little bit more about DPA. It's now being used in a number of academic papers. So there's that's a Google Scholar result for 280 academic papers. But if you go into some of them, a lot of them are actually using it as a solution to help capture the data, to analyze. And it also makes things a lot more recreatable, because you can exactly reproduce a setup based on just a few part numbers. So that's of interest to academic, of course, but it's going to tie into quite a bit of stuff that when you're doing cryptographic validation, you'll also want to be able to do. So as a question, if we're at this conference, if you're a well-paid test lab, why would you care about open source tooling? Why would you care about low cost? There's a few reasons that even larger companies and large test labs and stuff are still going to be really interested in this, I think. The first part is that because it's open source, you can actually modify anything you want. So if you want to use this for internal, that's fine. We have some people that have used some of the Chipwhisper hardware, for example, as part of automatic test suites that are running against algorithms, because they can change it to script with whatever type of device they're using, whatever language they're using. There's no restrictions there. There's no special API. There's no way for us to, for you to depend on specifically what I'm opening up. It's open source, so you can fundamentally change that stuff. The reason it's accessible is because there's even a $50 option, really. But the majority of the tooling is from this $250 to $4,000 range. And the point of this is not that, you're trying to do really cheap tests. The point of this is that if you want to actually set up a lot of these for automated testing, the cost matters. If you want to get people involved in this, that you wouldn't normally consider getting involved with DPA, especially if you have new hires, if you have interns, if you have research projects, for example, with universities. The tooling is probably not going to actually be the most expensive part anymore. Or if you have sort of other R&D projects where you have funding for them, again, the tooling is not going to be an issue for that. The other thing is that you might not actually be running this yourself. So you might not right now be interested in spending a ton of money getting a setup, but you would still like to be able to talk to whoever you're outsourcing this to. You'd still be able to understand, well, what are the effects of noise when you say there's too much noise? When you say, there's clock issues, when you say this, what do these measurements actually mean? What do these results mean? Well, the good thing is, if you spend a few days running some really simple attacks yourself, you actually understand a little more about how it works. So you can understand, okay, was this a really simple attack? Was this a complex attack? What does that actually mean in terms of complexity? So I really believe, that having that internal knowledge is really important. Even if you're not actually running the analysis or attack yourself, if you're hiring someone to do this, you should still be able to ask smart questions, and you should be able to understand what they mean when they're telling you things. So having done a little bit of work yourself can be really helpful in getting a better grasp on that. So it gives you a little more context to doing this work as well. When I say accessible tooling, so this is like an example from one of our distributors, our main distributor, Mouser Electronics. So it basically is that you can get physical hardware in 1 to 3 days on the open market. Most places in the world anyway, that is. There's the open source software, including tutorials, and as well as some different training options. So we've been working for some time to actually marry this ease of accessible hardware with some of the open source software, as well as an online training component that's now coming online. So if you're interested in spinning up, there's all sorts of ranges of things that you can do to actually understand DPA attacks. As another recent project that might be of interest is Chipwhisper and OpenTitan. So OpenTitan is this open source root of trust. So it's run by a nonprofit, low risk sort of consortium. So there's a bunch of companies involved, including Google's heavily involved. But it's not dependent on the companies. So the companies can't kill the project, basically. They're helping create it at this point. But you can use this in your own design. So this is pretty interesting. It'll eventually have the plan of having sort of countermeasured cryptographic implementations available in it. The end goal is to have physical silicon. So this will be a real chip that's really used in devices, but basically the objective is to have as much as physically possible be open source, right? Down to stuff that would not normally be open source involved in the actual production of the chip itself. So I have a sort of photo here, or not a figure here, from the documentation that's actually showing, they have a really nice, well, here's how the AES core works, here's how all the blocks work. You can go inspect the system Verilog and everything else. So it's quite a nice, reference for any sort of security work. It's now, so we've been working with the OpenTitan project to actually run a lot of the analysis on some of the Chipwhisper boards. So this board right here is an FPGA board that implements their current designs, right, as they're developing them. So you can then run some of the TVLA and other testings that you might want to run against these types of cores. So this is an example of a good resource, right, if you're getting started, because this is going to be a real project. It's not just some academic core that's not going to be used anywhere. We can actually use this as a resource for understanding how DPA works in real life. Related to that, I want to mention these calibration targets. So as part of FIPS 143, one of the things you might see in that involves some references to other specifications. So one of these specifications requires a calibration target. As an example, so there's some references in that to using different microcontrollers as well as using FPGA. So like this board here actually could be a good calibration target, because you could run say a specific crypto implementation like OpenTitan on it, and say, well, it takes X number of traces to leak. And the ISO spec goes through what some of those calibration standards mean. But basically, you need some physical hardware that we can compare between different setups to ensure we have consistency of setups. So these are one potential use here. So these are some of our target boards that I'm going to run some attacks on in a second. And I have a link here to a GitHub repo because these ones are actually fully open source as well. So it's open hardware. You can download the PCB files if you want and look at them, change them, make new ones, as well as having open firmware that's running on top of it. So again, it's a real concentration on making this stuff accessible to you. If you want to get started, some resources I'll point you to. So I'm going to run some tutorials from this Chipwhisper Jupyter repo. So this is an open source repository that has a number of sort of examples of different types of attacks, including fault injection as well as side channel analysis. Some of them already do or will be connected to actual real training material. So this is like more video focused training material that basically walks you through some additional material around it. But the resources themselves actually are available as part of the open source Chipwhisper project. Okay, so enough talk. Let's see how this actually works in real life. So I'm going to pull up here one of these examples. And what I'm going to run this on, just for reference, is I've got a few boards here. So this is, for example, a target baseboard, which has a we call this UFO, which has different microcontrollers that can plug into it. I'm using a Chipwhisper Lite. This could run on a Chipwhisper Pro as well. And for example, this would be like the FPGA. If you were running this in a system on a chip, like the OpenTitan stuff, you could run it on this board. And so this board would just replace here, right? So you can sort of see how this works. It's designed just to be pretty easy to switch between different types of targets. Okay, so if we run this, what you'll see is if I start at the top, it's actually going to build the firmware in this framework. So we could change the firmware if you want to try different crypto implementations. We're going to run software AES right here. So some of the targets have hardware AES. In this case, I'm running software. Obviously of interest if you want to try like different masking techniques and stuff like that. I'll program the target. And then we could do a bit of a capture. So we don't need many traces. This is just a software implementation. So I'm going to capture, say, 100 power traces. And so these are the AES power traces. You can see the capture is done there. It only took a few seconds. Okay, so the analysis, if I just run this block, what you're going to see is in red is the correct key. And you can see it pretty quickly filtering to the top, right? So this uses something to display called the partial guessing entropy. So let's rerun that, because what you'll see is after about in 25 traces, 25 to 50, it's correctly recovered the key. So this would be an example of a very fast, very leaky device. And we could use another, so in the actual, if you're interested in sort of the standards that are going to be used, there's a special leakage assessment methodology, test vector leakage assessment, that actually helps us understand how leaky it is without doing the full attack. So there are some tutorials on that as well, if you're interested in sort of seeing what that looks like. But the final thing here is I'll just run this, and what this is going to do is this is just going to plot the correlation. So this is showing us where in time the leakage is happening. So you can see really quickly, I just ran a CPA attack running on physical hardware, right? In this case, a software implementation implemented on a microcontroller. And we can connect to others, so there's connections to other open source toolings available. So there's some other libraries that can speed up your attacks considerably. But all that's available as part of some of this Chipwhisper stuff, running on this physical hardware. So hopefully this little quick sort of overview gave you an interesting look at what is possible with open source and low cost hardware and software. And if you haven't gotten started already with DPA attacks, hopefully this little simple demo will kind of kickstart you to get started and start exploring the field, because it's, I think really important for everyone involved in any sort of cryptographic testing to understand this and to understand it themselves. So not just outsource this to someone, even if that's your plan, but to understand what it means to the industry and how you can get started with it.